Okay, so angular motion next. The same ideas can be applied to something rotating in a circle. So if here's this rotation, we've got now not linear velocity. As this thing rotates around anti-clockwise, remember this idea of an anti-clockwise rotation about some center point. We talk about not linear velocity but angular velocity. And remember again, this letter, omega, please, not W. So don't refer to it as curly W, refer it to it as omega. Represents the angular velocity. We have now a situation where we've got the same sort of curve, but now we're not plotting linear velocity, we're plotting angular velocity against time. And again, we've got a situation where the angular velocity is increasing. So it's accelerating, a uniform acceleration as before. So we've now got a uniform acceleration. But it's accelerating in a rotation. You know, this rotation is increasing, the rate of rotation is increasing. And we call that alpha. So the acceleration is alpha. Same sort of situation. If I want to measure the total angle through which I've turned, the angular displacement theta, again, as before, the area under the curve between 2 points will give us the total angular displacement theta. So we've got exactly the same idea for angular motion as you have for linear motion. We define these terms as we did for linear. Theta, angular displacement, measured in radians, not degrees. Radians because the radian is part of a turn, as opposed to a degree, which is an arbitrary unit. Omega 1 represents the initial angular velocity. Omega 2 represents the final angular velocity. So omega 1 and omega 2 are the symbols we use for that. Alpha angular acceleration, as we've mentioned, and t time. And then we can write exactly the same equations as we had before in terms of angular displacement. So again, we have equations that we can write down. We can write down that the acceleration alpha equals the change in angular velocity omega 2 minus omega 1 over t. That has done it. Okay, so we've got alpha equals omega 2 minus omega 1 over t. Again, we've got that the average angular velocity, so omega average, equals omega 1 plus omega 2 over 2, which means that we can write that the angular displacement theta equals the average omega velocity, angular velocity times the time. So exactly the same that we had before. And we can now write down the equations of motion in terms of angular motion. So we've got, again, omega 2 equals omega 1 plus alpha t. We've got that theta equals omega 1t plus a half alpha t squared. And we've got that omega 2 squared equals omega 1 squared plus 2 alpha theta. The equations of motion, of angular motion. And again, we've got the same use of these formulae. In this one, there's no theta. So that's useful in problems where there is no angular displacement or we're not interested in it. No omega 2 and no time. And we could add this further one if we wanted to, which comes from these equations, the early ones, that the displacement theta equals omega 2 plus omega 1 over 2 times the time. So analogous, exactly analogous to linear motion. And again, we now need to have a look at some examples for how they can be applied.